So we looked at the cylindrical coordinate system, so now we're going to take a look at one final coordinate system other than rectangular, and we're going to take a look at the idea of spherical coordinate system. The spherical coordinate system is essentially predicated on the fact of a radius and then two angles that are swept from both the positive x and the positive z axes respectively. So there's three parameters that we're dealing with. We have the first parameter, which is the distance from the origin, which we're going to call rho. The second parameter we have is theta. And then finally, we have phi. Theta and phi are angles. Rho is the distance from the origin. All right, so rho is the distance from origin. Theta is going to basically be the angle swept from the positive x-axis. And phi is going to be the angle from the positive z-axis. So in reality, phi is the only new angle that we're looking at. If we were to plot one of these in 3 dimensions, so let's say for instance rho was 3, so we'd go out 3 units, and then we would have an angle. All right, so this is our theta, this is our rho, so this distance right here is rho, and then we would have a phi that comes out from the positive z-axis, and all of these would kind of link up, and what we're really getting is we're essentially getting a sphere, which is why they're called spherical coordinates. Okay, so maybe phi stops right about there. Theta is going to be this angle, and so essentially all we're doing is we're just taking this rho, which is going to be our distance, and we're just kind of sweeping that out somewhere onto the sphere. All right, so essentially we're probably ending up maybe like right about over here somewhere. All right, something like that. So it's a point somewhere on the surface of the sphere is what we're looking at. All right, there are some formulas for conversion back and forth between cylindrical, spherical, as well as rectangular. So we talk about the idea of x equaling rho sine phi cos theta. And if you were to take out that sine phi and replace rho with an r, it would actually look like r cos theta, which was what it was, which was what x was in cylindrical coordinates. Same thing for y. We're just adding in this sine phi. All right, so that might be an easy way for you to remember it, is just throw in a sine phi to what you already know from your rectangular or from your cylindrical coordinates. And then for z, that's just rho cos phi. So another one you have to memorize, unfortunately. These are pretty easy as well, except for the phi. So rho square is x square y square z square. This is a typo. I will fix that on your version. So that should be x square y square z square. Arctan of y over x is going to be theta, which was the exact same thing that it was in cylindrical coordinates. And then we have this nasty mess for phi, arc cos of z over root x square y square z square. Another way to think of this is you just find rho, and that's just going to be the same thing, because obviously if you take the square root of both sides, that's what rho is. So really phi, an easier way to remember it, is arc cos of z over rho. All right. There are some formulas that convert back and forth between spherical and cylindrical. All right. However, most of the time, if we can get to rectangular coordinates, that's sort of the bridge between the other two coordinate systems. So that's what I would recommend, just to make it easy on yourself. All right. So let's take a look at a couple examples to where what we're going to do is we're going to work back and forth between spherical and rectangular coordinates, and I'll illustrate how to plot some of these types of coordinate systems. So the first one we have, a really easy one in octant 1. We have the point 114 in xyz, and we're going to convert it into spherical coordinates. All right, so really easy to plot, so let's plot this first. So we have 1, and then 4. All right, so 114, in the xy plane. 1, 1 is right about here, and then we have our 4, which is going to be right about up here. All right, so just think of it in 3 dimensions. That's our point 114 in octant 1. And what we're hoping is that we can recreate that point in the spherical sense. All right, so remember that rho square is equal to x squared plus y squared plus z squared. In this case, that's 1 squared plus 1 squared plus 4 squared, which is 18. And that means that rho is going to be root 18 or 3 roots of 2. Now, rho is always positive. All right, so keep in mind that whenever you find rho, unless it's 0, which doesn't make much sense because then you're at the pole, then rho is always going to be bigger than or equal to 0 no matter what. All right. We know how to find theta. Theta is just the arctangent of y over x, and this one's really easy. So that's arctan of 1 over 1. You could throw that in your calculator, or you might know that arctangent of 1 is just pi fourths. Okay, since root 2 over root 2, or root 2 over 2 divided by root 2 over 2 is on the unit circle. It's the only place where it's equal to one another. And then for phi, remember we said that's the arc cos of z over rho, which is equal to the arc cos of z, which was 4, divided by 3 roots of 2. Now, this doesn't have a nice exact answer, so I'm going to stick this into my calculator just to kind of get an approximation. However, we'll use the real number answer once we get to us when we write the solution. Excuse me. I got 19.5 degrees. All right, so in terms of rho, theta, phi, we're going to end up with 3 roots of 2, pi fourths, and then arc cos of 4 over 3 roots of 2. Let's plot that. Okay, so we're going to make another graph. Now 3 roots of 2, I'll plug that in my calculator. 3 roots of 2 is about 4.2. So I'm going to move out 1, 2, 3, 4, and just a little bit more than that. We know that theta is pi fourths, so it's basically going to bisect it, maybe right about here. And then finally, we set about 19 degrees from the positive z-axis. So maybe really small. It's supposed to be curved, but it's not. We kind of follow that up here, and that's where our point ends up in octant 1. What you'll notice if you compare the two diagrams, they're very similar to one another. With respect to plotting, again, if I had a more refined tool to be able to plot this, it would probably look a little bit better. Probably not, because my handwriting's really bad. All right, what about the other way? Let's plot the point, 5 pi fourths, 3 pi fourths, and then we want to convert that into rectangular coordinates. All right, so not too bad. So we need our formulas. Remember that x is the same thing as x is in cylindrical coordinates, except we replace r with rho. We have our cos theta, but then we also have this sine phi that we throw in there. Y is going to be equal to rho sine phi sine theta. Sorry, that should have been theta. Get rid of this. Right. And then z is rho cos phi. Right. So literally, these are just substitutions. Right. So it's going to be 5 sine of 3 pi fourths. And notice that I have it defined. So phi is 3 pi fourths, theta is pi fourths. So just follow the parameters as they're outlined. Okay, so that's 5 sine 3 pi fourths, cos pi fourths. All right. We can certainly shove that into our calculator, but we can calculate it below. All right, we'll do that in a moment. We get 5 sine phi, so that's going to be sine of 3 pi fourths, sine of pi fourths. And then finally, we end up with 5 cos of 3 pi fourths. All right, so now remember, sine of 3 pi fourths is the same thing as sine of pi fourths because they're both above the x-axis. All right, so they're both positive, which means that that's going to be root 2 over 2. Cos of pi fourths is root 2 over 2. Cos of 3 pi fourths, because x is negative root 2 over 2. All right, so we get x is going to be equal to 5 times root 2 over 2 times root 2 over 2. All right, and that's just going to be 5 halves. Y, 5 root 2 over 2, root 2 over 2. That's another 5 halves. Z, 5 times negative root 2 over 2, and that's going to be negative 5 roots of 2 over 2. All right, now let's plot these both in terms of spherical as well as rectangular coordinates, excuse me. So let's plot it in terms of the spherical first. All right, so we had 5, right, and then we had pi fourths, so we're going to sweep out about halfway through, right, maybe right about here, and then we had 3 pi fourths, so that's going to go all the way down, and we're going to need a z negative, so that's going to go all the way down to about here, right, because we're below the axis. And if we line this up, all right, so we should have something. This is our angle in the xy plane, so it goes right about there. So we might have something somewhere around here. All right. Now let's plot it in terms of Cartesian. And we are going to need the z negative as well. All right, so 5 halves is 2.5. Then we have another 2.5, so right about here. And then we're going to move down negative 5 roots of 2 over 2. I'm just approximating this really quickly, and I got negative 3.5 approximately. So we're going to go down maybe right about here. All right, and again, if I had a little bit more refined tool, it might be better a plot. But what you'll notice is that both of the points end up about in the same spot, all right, approximately. Usually we use computer software to try to plot these sorts of things, but you should have a spatial understanding of where to plot these as well. So the final video, what we're going to do is we're just going to take a look at how we're going to convert these sort of spherical equations into rectangular and then plot them, much like we did for the cylindrical system.